Well, thank you for the introduction and welcome. I want to talk for just a few minutes this morning about robotics, try to give you an idea of what robots are, and explain how you can become involved with robotics, and hopefully explain why robotics are useful in society today. Okay? So what is a robot? It's a pretty simple question. Probably when most of you hear the word robot, you get an image in your mind that looks something like this, right? Robots have heads, they have two arms, they have legs, they look kind of like you and I. But you know, these pictures were all taken from movies or from comic strips or from other kind of popular media, right? So it turns out that there are real robots that look like this. We call them humanoid robots, but there's also a whole bunch of other different types of robots in the world, okay? So let me show you some real live robots that aren't from movies that exist today. So this is a humanoid robot. Like I said, there are some real robots that look like movies or movie robots, and this is a robot that was developed by Toyota. It's playing the violin. Why you would want a robot to play a violin is maybe another question. But it turns out this is actually a really cool demonstration of technology because it's very hard to make a robot play the violin. It requires these precise, graceful motions, okay? So maybe that's what Toyota is getting after. So this is a humanoid robot that was built by engineers. This is a totally different type of robot. This is a robot called Big Dog, built by a company called Boston Dynamics, and this is a walking robot. It's a quadruped walking robot, we would say. And it looks like a dog, sort of. A very kind of creepy dog, but a dog, right? And this is what we would call a mobile robot. It can move around, it can carry things, and actually the Army is developing this robot to help soldiers carry equipment. And you can see, you know, here's an engineer giving this poor dog a kick, and almost in a human or animal-like way, the robot can keep its balance and keep moving where it wants to go. So this is a really impressive piece of technology. Again, this is really hard to make robots that look and act like humans or animals. So, totally different type of robot. Now, down in the lower left, these are not mobile robots anymore. These are fixed-base robots, we would say. We call these types of robots manipulators. These orange robots here are working on an automotive assembly line. They're welding the body panels in your car. So your car, the car that you drove here today in, was basically constructed in part by robots. And so you think, okay, this robot, you know, can't move around. What good is it? Well, it's very good at doing very precise tasks within its workspace. It can reach out and grab things, weld things very, very precisely, and do the same thing over and over for many, many hours. So this robot will do jobs that human beings are not very interested in doing because they're very repetitive, they're boring, they're dangerous. Totally different type of robot than the first two robots I just showed you. Okay, two more examples. Look in the lower right. This is a robot with a subtle name of Crusher. It's developed by Carnegie Mellon University. It weighs about 8 tons. It looks kind of like a military vehicle, doesn't it? But if you notice, there's no crew cab. There's nowhere for someone to sit and drive the vehicle because there's no driver. So instead of the crew compartment, there are sensors, and the driver is either sitting, you know, a mile away looking through a video screen, or there's no driver at all. It's what we call an autonomous robot. It drives by itself. All right, so you know, why would you want a robot to do this? Well, if this is going to be engaged in activities in a dangerous area like a military environment, well, you're reducing the risk to a human operator, and that's one of the big advantages of robotics. So this is Crusher, another mobile robot. So last example, robots move on the surface of the earth. They also fly in the air, and they can travel underwater. This is a robotic snake that was developed by researchers in Japan. It looks like an eel, doesn't it? It's got a really almost beautiful, very graceful motion. And again, this is really, really hard to make a robot that's constructed out of gears and bearings and mechanical parts and have it move in such a graceful and elegant way. And it can do this because it's got very intelligent software, and I'll talk about that. So 5 different examples of totally different types of robots, only one of which looks like a movie robot, but these are all robots that engineers are developing today. Okay. So let's try to find a general definition. So what is a robot? I've shown all these different examples. Generally speaking, a robot is a device which has a mechanical structure of some type, and it has sensors, actuators, and software. So what are all these things? Let me tell you about them. So sensors. Sensors are just devices that allow a robot to measure some information about the world. They allow a robot to see, feel, hear, and maybe even smell, something about the world. Why would a robot want to do this? Well, a robot might want to see. If you think of the crusher robot, the wheeled robot you saw on the last slide, you'd want to see what's in front of you so you know where it was safe to drive and where it wasn't safe to drive. If you were driving on a road, you might want to distinguish between the surface of the road, which might look a certain way, and then the shoulder of the road, which might look another way. So video cameras are actually very useful sensors for robots. The video camera in your cell phone, it's the same type of sensor. And we apply some software processing and we can tell where it's safe for the robot to move and where it's not safe. There's another type of sensors called LiDAR sensors. Most of you probably don't know what a LiDAR sensor is. It's a sensor that emits a small pulse of light, and then it detects the reflection of that light, and it measures how long it took to detect that reflection. And since we know how fast light travels, we can calculate the distance to that reflected point. And we do this many, many times, a lot of times, right? So here's an example of a sensor, a LiDAR sensor that was mounted on top of a vehicle. This is the data it collected when we were driving through Cambridge, Massachusetts, where I live. And all these little points represent the distance measurement from that sensor to some point in the environment. And if you look at it, you can kind of, pick out the surface of the road. We're driving down a city street. You can pick out the surface of the road, the flat areas. You can pick out the presence of cars here. You can see where there are some trees or maybe some tree stumps. So you can imagine if you were a robot, you might apply some intelligent software to be able to understand where's the road, where is it safe to drive, where is it not safe to drive. So this is a LiDAR sensor. This sensor, in particular, measures 1.2 million data points per second. So you need some pretty intelligent software to process all that data and be able to act on it. And there's other types of sensors that measure things like force. If you were maybe picking up something or squeezing something, touching something, you might want to measure how hard you're doing that. Microphones to measure sound, and as I mentioned, even sensors for smell. So the other main component of a robot is the actuators. Actuators are what allow a robot to move, to actually do something. If you don't have any actuators, the robot's just a big paperweight, right? So actuators are usually either, we'd say linear or translational, which means they move back and forth, or they're rotational, which means they move, they turn, all right? So this video here shows some robots on an assembly line, like the video you saw a few moments ago. They're doing an inspection task. They're not doing welding here. But they're, again, these robotic manipulators, as we call them, or robotic arms. And if you look where the pointer is, kind of the shoulder of the arm and this elbow joint of the arm, these have actuators, rotational actuators, that allow that joint to rotate. And then if you coordinate the motion of all the joints, you can make the end point of the robot go exactly where you want it to go. So you don't think about this as a human, you just reach out and grab something. But if you think about programming a robot to do that, you'd have to coordinate the motion of each of these joints. And what you're doing is powering these actuators in a particular way. So actuators can be electromechanical, which means a motor, which you apply a current, and the motor output shaft spins. It can be hydraulic, which means it's powered by some type of fluid. They can be pneumatic. A pneumatic piston is powered by pressurized air or some other gas. And they can be artificial muscles. People are working in laboratories to develop actuators that are like the human muscle, like in your bicep. Human muscles are very, very lightweight and very strong, so they would be great to use for robots. Okay, so the third part of a robot is the mechanical structure. Obviously, you need something to hold the sensors and the actuators, and the mechanical structure really defines where you can use the robot and what it's going to do, right? It seems kind of obvious, but let's say you had a given environment that you wanted to apply a robot in, some rough terrain, some rubble environment you want a robot to travel across. Depending on how you design the robot, your system will either perform really well or maybe not so well. So let's compare these two different examples of robots with very, very different mechanical structures. One is a snake, which is kind of shooting across the floor, kind of wriggling across the floor. This was developed by a group at Carnegie Mellon. And the other one is what we call a hexapod, which means it has 6 legs. It looks kind of like an insect, right?